Hi, I am Mr. Tsevi, and today I'll be teaching you linear algebra on linear map. We say that V and W are vector spaces over F. So we define a linear map. We say that a function T which maps every element in the subspace of V to all the way to every element in subspace of W. It's called linear if two conditions are met. First condition, we say that T in U plus V equals to T in U plus T in V, whereby T, U and V are subsets in the universal set of V. And then we also say for a scalar, we say that T in AV equals to A into TV. I can just put brackets here. Into TV, whereby A belongs in F and V belongs in a universal set of V. So we have types of linear maps. Number one, we say the zero map. A zero map, it maps every element from V all the way to every element in W. And we say that V and W actually belongs to the universal set of V, but 0 belongs to W. And then if 0 belongs to W, it means that this condition, this thing is linear. It's a map, it is called a zero map. And then number two, we have identity map. Identity map, like I said, it maps every element in a vector space of V all the way to V. It is defined as identity map of V equals to V. Then this is linear. Identity maps, an example of identity maps, it can be r squared all the way to r squared, whereby T will be a function. Let me erase and explain these things better. Example. We say let T P of F all the way to P of F be differentiation. Be a differentiation map. Defined as Tp of Z. When we differentiate this, we get P of Z. This is what we are getting. So, for two polynomials, Pz and Qz, which exist in P of F, they actually exist here. We say that T into P of Z plus Q of Z is equals to P of Z, Q of Z. When we add these polynomials, we must also differentiate them. And when we differentiate them, we get P prime of Z plus Q prime of Z. And this brings us to the first condition. So this means that this will be Tp of Z, and then this one will be Tq of Z. And this can be written as T P of Z plus Q of Z, according to the first condition that I've given. So also for a scalar, we can do the same. we can do the same. But for a scalar, we know that TA of PZ equals to this one is a constant. I can take it out and differentiate P of Z, whereby it will be something like A P of Z. But this one is the same as A T P of Z. And this can be written as TP AZ. It can be written in this fashion. And this thing is equals to this one. So, if we are having two polynomials which are added together, or three polynomials, if we can write them this way, and then again we write them this way, then we say that that particular function, it is a linear map. So in this case, T will be a linear map. Let me take a real life example. Let's say that we are given an example and they say that we must prove that T is a linear map. So firstly, we are going to consider the first condition, but we are going to consider xy and x prime of y prime, which belongs in EV. They belongs in the universal set of V. So wherever I'm seeing x, I'm going to substitute xy. I'm going to add this together. So I'm going to have T xy plus x prime y prime which will be equals to x plus x prime y plus y prime. We are going to write it like this. So, but this is equals to this, and this is equals to this one. So, since we proved for LHS, we must also prove for RHS. So my RHS will be that function. But wherever I'm seeing x, I'm going to put x plus x prime, like I'm given here. And wherever I'm seeing y, I'm going to put y plus y prime. Even here, x plus x prime, y plus y prime. This is what I'm going to put. So, I can multiply throughout the brackets. Two y minus 2y prime 3x plus 3x prime plus y prime. So we must actually write this in this manner. We must write this in this manner. Let me show you. We are going to say x minus, we are going to take 1x here. Let me do this. We are going to say x minus this one. And then again we write this, because if we are writing this in terms of this one or this one. So we took this one and this one. So right now we are left with this one and also this one. The trick is to write this in terms of t, x, and y. This is the trick. This will be here. I can just remove these brackets and write this. So in this part, I'm considering the ones for derivatives. So I'm going to take this x prime and then also with something prime, which will be this 2y prime. Or I can just erase those brackets. Actually, I can just erase those brackets. So here I'm going to take this one and this one. Sorry, this one and this one. It will be 3x plus y prime. This is what I'm having. So this side, we can see that it can be written as t prime of y prime. We can clearly see that. So this will be the same as t of x plus t of x prime y prime, which is the same as t of xy plus x prime y prime. So this thing is equals to this thing or this one. It can be written, this one is equals to this one. So is equals to LHS. This one is equal to this one. So the first condition is met, since we can write this function in terms of this. So, but we must also consider when it's a scalar, when it's multiplied by a scalar. So let's consider this for a scalar, since the first condition was met. So we'll consider this. We'll not consider the derivative this time. We'll consider this, where a belongs in f. So if I will write it like this, I will multiply by a inside. So wherever where I see x, I'll put a. Wherever where I see y, I will also put a. I mean, wherever I see x, I'll put ax, and wherever where I put I see y, I put ay. So here I'm going to put ax, and then here I'm going to put minus 2ay, and here I'm going to put 3ax, and then there I'm going to put ay. If I factorize a, I will have x minus 2y, 3x plus y. We can see that this is the same as x, y. So I can substitute by this. But this can also multiply through all the brackets, since it is a scalar. So this one is equal to this one. Therefore, T is a linear map. So guys, this is the end of the video. If you liked it, you can subscribe and then hit the notification bell so that when I upload, it can actually notify you. Thank you.